Recursive formulas. So up until now we've really worked with explicit formulas, and an explicit formula allows us to find a certain number of a sequence and go straight to that number. So I would be able to find the 20th term of a sequence, I could find the 100th term of a sequence without finding all of the terms before that. A recursive sequence doesn't work that way. So a recursive formula allows you to find the nth term of a sequence by performing operations to one or more of the preceding terms. So the classic recursive sequence is the Fibonacci sequence, where in order to find one of the terms, I need to know the terms that are preceding it. So I start with 1, I'm going to add 1 to that and get 2. I'm going to add the last two terms, 1 plus 2 and get 3. I'm going to add the last two terms and get 2 plus 3 get 5. I'm going to add the last two terms, 3 plus 5 and get 8. So I need to know the terms that were preceding it in order to find the next term. So that's our classic recursive formula, recursive sequence. We're going to look at formulas that explain what the sequence is and allow us to find the next term. So we're going to find the first 5 terms of each sequence which, and here's what our recursive formulas look like. They're going to describe the first term to us. So they're going to give you the first term. And then they're going to give you a formula. So we've seen this before. A sub n, meaning A, meaning whatever term you're talking about, and n meaning the number of the terms. So I might want to find term 2, term 3, term 4. We've seen that before with our explicit formulas. We're going to take 3 times a to the n minus 1. So whatever term you're looking for, subtract 1 for it. So a to the term before, whatever the one you're looking for it is. In this case, subtract 12 from that. If n is greater than or equal to 2. This simply means that we're not going to start with the first term. So whatever term we're looking for has to be greater than or equal to the second term. I can find the second term using this formula. I can't find the first term using this formula because then I don't have any term to start with. So it needs to be given the first term. We need to know that this formula works for at least the second term, and then they're going to explain what's happening in the middle. So let's find the first 5 terms of each of these two sequences. So what I've got here looks like a ton of work. Please know, as I always do, I've kind of really given you every little blip that happens along the radar as we're going. We'll start to condense it a little bit as we go. So it still looks like a lot of work, but it'll be a little bit less work as we go along. But I really want to show you what's exactly happening. So our first term, a sub 1, is 7. For our second term, I'm going to use the formula that they gave us. I'm looking for the second term. They told me to take the n out and replace it with a 2 because I'm looking for the second term. So 3 times a, 2 minus 1, minus 12. All I did here was substitute 2 in for n. Now I'm going to do this 2 minus 1 and I get 1. So basically what this says is your second term is equal to 3 times the first term minus 12. That's really all these steps did for me. It just really showed me that, okay, all this formula wants me to do is do 3 times the first term and then subtract 12 from that. So the first term was 7. So I'm going to do 3 times 7 minus 12. I'm going to get 21 minus 12. I'm going to get 9. So my second term is 9. First term 7, second term 9. So far so good. Now to find my third term. I'm going to take my third term and I'm going to do 3 times. I'm going to multiply it by the term before it. So that's all this is having us do. This n minus 1, what term do you want? I want the third term. Subtract 1 from that. That's 2. You're going to use the second term in order to find the third term. So I'm going to do 3 times the second term minus 12. The second term was 9. So 3 times 9 minus 12, that gives me 27 minus 12. That gives me my third term of 15. All right, so now that I've seen the pattern, I can do a little bit less work here. My fourth term is going to be 3 times the third term minus 12. Third term was 15, so 3 times 15 minus 12. That's 45 minus 12. Fourth term is 33. Fifth term, we're going to do 3 times the fourth term minus 12, which gives me 99 minus 12, which gives me 87. So my 5 terms are 7, 9, 15, 33, and 87. A lot of work. But recursive formulas tend to work that way. They tend to be a lot of work. All right, next sequence. A sub 1 equals negative 2. So my first term is negative 2. A sub n equals negative 3. A sub n minus 1. So again, here is that. Take the value of the term before this. So this just means the term before it. Plus 4 if n is greater than or equal to. So again, this is my first term. This just says this only works if I'm starting at the second term. And here's really the meat of my recursive formula, which shows me what the pattern is like. So here's my first term. My second term is going to be negative 3 times my first term plus 4. So negative 3 times negative 2 plus 4. That's 6 plus 4, which gives me 10 for my second term. My third term is negative 3 times the term before it, which was 10 plus 4. So negative 30 plus 4, third term is negative 26. My fourth term, I'm going to take negative 3 and multiply by the term before it and add 4. So I get 78 plus 4, which is 82. And then for my fifth term, I'm going to do negative 3 times the fourth term, the one before it, which is 82 plus 4. I get negative 246 plus 4. So my fifth term is negative 242. So this is what this sequence looks like. Negative 2, 10, negative 26, 82, negative 242. So again, the three parts of this, we're going to say the first term. Next part is going to tell me what's going on, what's the actual pattern here. And the follow-up is just going to tell me that I can't start with a term before the first term because they gave me the first term. So I'm going to only be able to start with the second term. All right, so let's actually put together some recursive formulas. So writing a recursive formula, there's three parts to that. So the first one you need to do is determine, is this arithmetic or geometric? We've looked at arithmetic and geometric. Arithmetic sequences, we are adding the same thing to the term before it. Geometric sequences, we are multiplying. So it's determining whether we have a common difference or a common ratio. So once we've determined whether it is geometric or arithmetic, we're going to write the formula. So for an arithmetic sequence, we're going to say a sub n equals a to the n minus 1 plus d, where d is the common difference. Remember, our arithmetic sequences have a common difference. Our geometric sequences, a sub n equals r times a to the n minus 1, n minus 1 sub n minus 1, where r is the common ratio. So here we're going to use our common ratio and multiply the term before it by that common ratio. And here we're going to use our common difference and add that to the previous term. And our third step, we need to describe the first term, and we also need to state the domain for n, which in all of these cases is going to be that I can't start before the second term. So n is greater than or equal to 2. So we're going to find a recursive formula for each of these sequences, 4, 10, 25, 62.5. So I'm going to see, is there a common difference or a common ratio? So first I try subtracting. 10 minus 4 is 6, 25 minus 10, that's not 6 either. So let's try dividing. 10 minus 4 is 2.5, 25, let me try that again. 10 divided by 4 is 2.5, 25 divided by 10 is 2.5, 62 divided by 10, by 25 is 2.5. My brain's not working. So I have a common ratio of 2.5, which means this is geometric. So what my pattern is going to look like, I'm going to start by describing my first term, which is 4. So a sub 1 equals 4. I'm going to put the pattern together here. So a sub n equals 2.5 times a sub n minus 1. So again, I'm multiplying by that common ratio if n is greater than or equal to 2. So once you find that common ratio, it's just a matter of plugging it into what the formula looks like and describing the first term. Pretty straightforward. Next one, 9, 36, 63, 90. So again, I'm going to try subtracting. 36 minus 9 is 27, 63 minus 36, 27, 90 minus 63, 27. All right, so since I have a common difference, this is arithmetic. So it's arithmetic. My common difference is 27. So I'm going to describe my first term. My first term is 9. My pattern looks like this. A sub n equals a sub n minus 1. And then I'm going to add on my common difference here, which was plus 27, if n is greater than or equal to 2. So I'm just going to describe that I have to start with the second term. And the last one from a word problem. An assembly line can create 175 widgets in 1 hour. 350 widgets in 2 hours, 525 widgets in 3 hours, 700 widgets in 4 hours, and so on. So this is what my pattern looks like. 175, 350, 525, 700. This is arithmetic, because if I subtract, I keep getting 175. So I'm done. Don't need to worry about it being geometric, because it's clearly arithmetic. So my pattern is going to look like a sub 1 equals 175. That's my first term. And here's my pattern, a sub n equals a sub n minus 1. I'm going to add on that common difference, plus 175, if n is greater than or equal to 2. So that's what my recursive formula for this particular pattern looks like. So again, thinking of recursive formulas as only being able to find the next term by using the terms preceding it. Again, in case of Fibonacci, I need the 2 before it. In case of the ones that we've worked with here, I just need the 1 before it. 3 parts to each of those formulas. I need to know the first term, I need to kind of know my pattern, and then I also need to explain some domain for our n, so our recursive formulas.